how many people in the room know about Arrow in general? Oh, shit. Nice. It's extending. Cool. This is a talk for everybody else. So now, it's a talk for everybody. So the main idea is to pick up a little bit to where we left after KotlinConf last year. So we made a promise. We said that we were trying to grow our tools. We tried to improve our ecosystem, and we wanted people to get more involved with it. So this was not an exercise in isolation. This was something that we wanted to create, like a small community where we were trying to improve the way that we are doing Kotlin. So the main talking points for today is where does Arrow fit in your day-to-day code? So this is not only for the people that already use it, it's also for the people that are considering it or that don't even know or understand what Arrow fits in their development. The second one is, for those who are already using it, where are the more advanced contracts that are available, the ones that we're working on right now, and the ones that should be available in the near future. And lastly, we're going to go through how the community has been growing, what new projects have popped up, which people are using the library, and the way that we are engaging, basically, with everybody else. So our first talking point is going to be about how we're trying to build a functional intuition. So when I talk about functional intuition, in this case, I'm going to be using one example. A couple of weeks ago, we had a release of the version 0.7.2, where we had like a new DSL that I'm going to be explaining later. The point is, somebody in the comments just went and said, hey, I believe that the code that you're promoting is not readable. It's like, because everything that you're doing right now can be done by this snippet. And he had a certain good idea or good starting point in the sense that you can go through this code and you can understand what it does, right? It's something that everybody has seen at some point. So let's go through it for a second. We have a new ArrayList. We're going to have a list of talks inside a meetup. For each one of the talks, I have to go through the list of assistants. And for each one of the assistants, I'm going to be updating their IDs with a function. So all of this, it is done in an immutable structure just so I can update the ID of each one of the attendees. So we're doing one for loop, two for loops, two additions, several copies, and everything else. And this is code that is really readable because you go line by line and you understand what he's saying. But for me, the word readable is a little bit overloaded, so I prefer to use the word familiar. So this code is actually not readable, which is very subjective. It's familiar, which is also another subjective term, but it doesn't try to cover itself as an objective term. So what does this mean? It means that if you understand what is familiar to you, and this is what is familiar to you today as a Java developer, this can also become familiar. So we're going to have the meetup, we're going to copy it, and actually we're going to map the list of talks. And then for each one of the elements of the talks, we're going to map the list of attendees. And for every attendee, we're going to copy it, and we're going to update it using a function. How many people in the room would feel comfortable, will feel familiar with writing code like this right now in Kotlin? Exactly. Roughly half of it. Why wouldn't this become familiar at some point? There's a meetup, which is a companion object. From there, we're going to get another element called talks. We're going to say for every one of the talks, we're going to see the attendees. For every one of the attendees in every one of the talks, we're going to get the ID. And then we get a block. And inside the block, we have a set of extension functions to update that ID. So we're, to update that meetup, and in this case, all the way down through ID. So you can say, hey, here's a meetup that now has an extension function called modify that takes a function from ID to ID. So basically, you have opened up a scope where you can do these transformations as if they were mutable fields within mutable fields. And all the copy, traversal, map, and everything else is being done for you behind the scenes. So I believe that this is something that can become familiar to people. So we have to go through a couple of myths and misconceptions. When we're writing that code, this is something that was put into place by Eugenio's library from this morning. So when he was discussing like all these mutable, like very deep updates and everything else, this is actually being powered by code generation. But this is code that you could write yourself, because each one of the layers Each one of the traversals, each one of like mapping and everything else is actually a single function, which is a setter. If you can write an interface with a setter, you can compose each one of the setters all the way down the same way that you compose functions. So we are not doing bytecode, we are not modifying the AST, we're not doing anything that is out of the ordinary. We're just using simple principles to build more complex like use cases, basically. But the build-up pieces are always the same. The second one is when people say, hey, I've done functional programming before, I've been using RxJava, and it's really complicated because when I go to debug it, there's a bunch of like queues and operators and new classes and everything else, and I have to look into the stack traces. And my point is that all of that is engineered for a streaming library. The streaming library is supposed to be multi-threaded, it's supposed to have back pressure, it's supposed to have like zipping and everything else, it has queues, it has all this machinery behind the scenes so it can do what it's supposed to do. Functional programming is actually a simpler version of this, with simple going functions, calling functions, calling functions. But none of that is actually jumping threads, there's no handlers, these complex concepts are not necessarily part of functional programming, they are part of a single library. The third element is that, okay, how do I test this? How do I test this single meetup talks, every attendee, every ID? Actually, this is a single function, and the function takes a meetup and a function from ID to ID. So in every single place where you would need this function, you can actually pass it as a parameter. Oh, I'd rather just pass something that is returned by meetup, all the way down to ID. That's actually an interface that goes from meetup to another meetup. And the transformation can be whatever you want. So in this case, it would be updating the ID, so you can just create like a new meetup and put all the IDs in there, whatever way you want to mock it. So you're just mocking a single interface, or you're just mocking a single function, and that's everything that you need for testing. You can just replace this long construct with a single function from meetup to meetup. The other one that we get is the most common question ever, which is, how is the performance? And how is the performance is a really loaded question because you can break it down into several different parts. The first one is, how is the runtime performance? And to be honest, the runtime performance is the same one as if you wrote it yourself. So if you're composing function one after another, if you're writing a map to a new element, to a new copy and everything else, if you can abstract that, that's your runtime cost. Whether you write it yourself or we write it ourselves in the library and we provide it to you. So we are giving you a way of abstracting these issues in a way that they are reusable. Okay, Paco, but then we have to do a little bit of annotation processing. And annotation processing is slow, it doesn't cache, it does everything else. And that is correct. There's a compile time performance cost that can be assumed. If you don't want to assume that compile time cost, the good part is that most of these constructs are stable. So once the library is stabilized, the API is not bound to change. So that means that you can compile them once, you can add them and check them out into your code base, and you can reuse them for all time. We're not going to be like performance optimizations or anything of the sort, because it's actually just function calling functions. There's no performance optimization that can be done on top of it. So if you check it out, and maybe if there's an API change, you're going to be automatically told, hey, the interface that you implemented, that you have checked out into your code base is the wrong one. Use the annotation processor once more, copy the data over, and then you just have it forever. So basically, it can be cheapened if you don't need the annotation processing. So the compile time performance, it is real, right? Something that can be addressed. The next one is, what is the development time performance? And this is the key concept that we are trying to focus on. How do we make people faster? So instead of having to write an array list that have to traverse, that have to write a for, that have to copy the fields and everything else, how we can make people faster so they can only think about the ideas that they are trying to codify. In this case, updating a field that is deeply nested. So this is a huge win. This is where we see the most wins. This is when I go to a company where I'm working day to day and people tell me, hey, you're pushing out the most amount of divs. This is the, you're providing lots of values because I'm not thinking about, am I moving through this? Like I said a for and then I put a value outside and then I have to do to list in the end because it requires a mutable list. I don't have to think about any of that. I write it once, it works, and I'm just delivering value the rest of the time. I'm just thinking about like my deliverables. And the last one is the debug time performance. So what happens? We don't have the queues. That's right. We still have functions calling functions. The good point is all of this implementation is canonical. So you only have to take a look into the entry points So the information that you're actually passing into your functions, your configuration points are the only ones that are fillable, because everything else is deeply tested for all possible use cases. We try to write total functions that just traverse the whole thing. Cool. So this was the first thing that I wanted to get out. So we are trying to build something that is useful to the people so they can focus on actually delivering information and a little bit less in accidental complexity. So how do you tackle the ordinary with Android? Basically, you're going to start thinking about your API design concerns. This is the most basic thing that you do day to day. Hey, I don't want to write a new class every time I have multiple returns from a function. So the second one is like, what happens if my function has to fail, has to throw, is not total, it cannot handle all possible input cases, or maybe it can throw an exception. Do I need a function to be lazy? Do I need a function to cache its results? Do I need a function to be executed every single time that it is called? Or, even if my Android app cannot take a single more library, we can still provide you with something that is a core, that is the very minimal implementation that is going to be helpful to you. And that's the ArrowCore. ArrowCore is a simple starter library, so you're going to be seeing those indications at the top about more or less the level required to use these constructs. Doesn't mean that when you use the Arrow library, you have to use everything else. You just pick and choose the ones that are important to you. So in this case, when you had to, instead of writing a new class for a multiple return, you can have a tuple. We have tuples all the way from 2 to 21. They have like aggregation, they have functions, they have constructors, they have everything that you need from them, they already provided to you. My function returns a fail or throw or a branch out. It has different ways of happening. It has to do error handling, but I don't want to do it myself because I'm a library, or maybe I'm at my API layer or my domain layer, and I want the layer above myself to decide what to do, whether display a UI on a screen, whether to display a different string or something else. So what do you do with that? You have either, you have try, you have option. You say this function find on a list, if it finds an element with a Boolean, it's going to return an option of a tuple of the position and the element itself. The next one is I need a function to be lazy or cache its results. We have a simple class that is called eval. You can construct an eval with a single function that it can capture its context, and it can just memorize its results. It can be cached. They can be lazily evaluated. You can do many things with it. And basically, we're using this for folding right. For example, in folding right is an operation that can actually be a Stack Overflow, because you can be traversing an instruction indefinitely and never finish. So we use eval to notify that a function has no termination, or it reached a point of termination without throwing that exception. So it's kind of like a trampoline, if you know about tail recursion. And coming from these same ideas, we have another library. This one is a little bit bigger. This one contains some more constructs that can still be useful to you. And that's the Arrow Data module. Arrow Data basically has a little bit more focus on collections. So you can have non-empty list. You can have wrappers over list, over map, over set, where we're going to be adding new functions that are going to be useful, that do operations that are common to your day-to-day. I'm not going to go too in-depth to it because I don't have enough time, but we're going to see some examples later. There are another different kind of functional constructs that are called the reader, writer, and state, which is a functional way of like writing to logs or getting dependency injection or just having transformations as you're traversing your program. And then there's like composing data types using monad transformers, but nobody wants to get into that. That's a little bit more advanced, but it's also part of the Arrow data. Another different part of the Arrow library, of the Arrow ecosystem, is actually the library that allows us to use functions. So let's write the code for a second. We have 3 example functions. The first one takes an int function from int to int. It takes an int, it gives you 1. The second one, it takes an int, it returns a string. Int to string. The third one, it takes 2 ints and returns a third integer. Why? Because it's adding them together. Cool. How not to handle the functions like data? So this is just going in a way that you're going to be rewriting. You're going to be repeating yourself every single time. You're going to create a new lambda, and you're going to say this function has to call this other function, has to call this other function, and they keep composing in that like this deeply nested set of functions. So you can compose the integer with the integer to string with the result of the integer to integer, so you're actually reading them differently. You can compose the two functions from integer to integer with the result of the sum. So all of this is just basically you're just writing a lot of code to do simple compositional operations. And the last one is a funny one where you say, hey, I'm actually going to ignore one of the sides. I'm going to return a function that takes a single integer and adds 10 to it. So arrow syntax is a module that is basically its only use case is doing function composition. We're going to see each one of the use cases. The one at the top, you have function from integer to integer, and then another function from integer to integer. So basically, you're doing the same thing as in here, from end to end, both ways. You pass a 0 to that function, actually returns you a 2. Each one of them sums 1, it gives you a 2. We have a function that is from int to string, and we want to compose it with an int to int, which means it's going to go the other way around. You first execute the function that returns an int, and you pass it into the function that returns a string. You use compose for that. So you can do composition that goes the other way around as if you do and then. You pass a 2 there, and it returns actually a 3 string, because he has done both operations. The third one, we have a function from int and int to another integer, so a function with 2 parameters that returns 1. You can just say and then with one of the parameters, so you're composing the function, even if the first one takes a single value. You could still compose it with a string one, it will still work the same, because this is just like piping functions, basically. And the last one is, I have a function with 2 parameters. I'm going to pre-apply one of them. So I'm going to be returning a function that takes a single parameter. And that single parameter is actually going to be 10. Sorry, 10 is the parameter that is fixed, and 2 is the one that I'm passing. 10 plus 2, 12. That's the final result. So you're just having all these helpers, so you can think, instead of thinking about, like, I'm creating the lambdas and I'm calling this information, you start thinking about, oh, I'm actually composing functions. I'm composing it in one direction, I'm composing it in another direction, I'm actually removing one of the requirements because I already have the information available, like the context, for example. Or maybe you have something that returns a tuple, and you want to pass it into a function. You have one way of doing it, which is deconstructing, or you can do it the other way around, transforming the function so it takes pairs instead. So there are ways of transforming these signatures and this data. And the last one is just memoizing. Memoizing means remember the results for a single parameter. So you can have like a map that is caching. If you pass a 3, it remembers that you have to return a 4. If you pass a 5, it remembers that it has to return a 6. And every time that you call it, it's going to return the same value. And the funniest thing, you see that arrow in there, 0 arrow, 2 arrow, 3 arrow, 2, 3 arrow, and everything else. That is actually called a pipe. It's another kind of function. And that function, what it does, it takes a value, it takes a function, it's infix, and it applies the first value to the function. So you can have different ways of writing your function, composing them, and working with them in general if you use the arrow syntax module. And this is all starter level, basically, because it's just moving functions around as if they were data. So these are the most core basic information. You can get this into your library right now, and this tackle the small problems. Your day-to-day code, your small functions, your API returns, and everything else. The next part of the talk is going to be more focused on the bigger ideas, on the larger constructs that we make out of the smaller ones. So we're going to start with the first one, and it's the one that we've been announcing, the one that I've been showing in the slides and everything else, which is how do you want to do plain data? You have structures that are now immutable. You have collections that now you have to access the elements. You want to traverse them. You want to access a single position. You have a map. You want to access a value for a single key. Or maybe you have sealed classes, and you just want to use every single, or just one of the possible values. Or maybe you have an option or an either inside your data model, and you want to do something only if it contains a value. So we're going to do a throwback slide. It's the same one as before, meetup talks. Every single one of the talks, because it's a list, attendees, every single one of the attendees because it's a list. So each one of these is actually something as simple as function composition. It's functions all the way. So you have something that is called an EVC ID setter. An ID setter is actually an interface that has a single function set that is composed with a list of each, which means you're going to be able to traverse a list of attendees, which is composed with an attendee setter, which is composed with a list, which is composed with a talk, which is composed with a meetup. So it goes all the way down. Or we could just go and say meetup setter, and then tag setter, and then list each, and then. So you do the same way that you do function composition, you can compose interfaces that have one or multiple functions. But I don't want to write those, right? Because that's a lot of boilerplate, and I have to do it all the way down. So if you saw Eugenio's talk this morning, he had one that it was called optics, and that's our annotation. So you go with that annotation, you put it in our CO class, in this case, which is called a network result. We have a success, and we have an error. And actually, error is another different CO class with an HTTP error or just a timeout error. So we have these two different sets of CO classes, and each one of them has multiple values. Boom. Network result, that succeed, that meetup talks every attendee, every ID, get result or modify, which is basically says, hey, if I'm not able to actually get this information about the ID because, I don't know, the list is empty or something like that, then just give me the original list. So you get something that looks like an API with either, instead of just like failing or throwing an exception. Oh no, I want to go through a different branch. I want to go through the error branch, to the one that goes through exceptions. Network result dot network error, which is the use case, is the part of the when. The same when that success is the part of the other CO class that you would usually do with when. Now you can do it simply as if you were accessing a field. HTTP error dot message, and I can just get the message. I could also modify the message if I wanted to. So all of this belongs into the package called ArrowOptics. ArrowOptics cares mostly about whether do I need to access a field, whether I need to change the values of that field, am I accessing a collection, am I accessing one of the different branches of a CO class, or maybe I want to go into a single key inside a map. So it has helpers, and it has code generation for you to be able to transform this data and work with this data in general in your code. So you don't have to worry about accessing these pieces, looking for that user that is deeply nested or anything of the sort. You only have to actually care about the business logic that is required for you to deliver value. Next part, this is a little bit of an advanced topic. So this is more of a calling out people in the room. If you ever see your data structures that start looking like that, so you're going to have a list of multi-projects where you have a single project, and then you have another nested multi-projects that has every single project. And actually, well, we're going to be using non-empty list to signalize that actually none of this can have no projects at all. So multi-projects actually is a list with at least one element. So we're using our own collections here. If you ever take a look at the data like this is actually a tree. It's a tree-like structure that can be written in Kotlin like this. CO class of a project of an A. A, in this case, it's going to be a value that is parametric. We're going to have a name of the category for multi-projects, and then we're going to have the list of projects. And every single project has a name and has an information attached. And in this case, because A is parametric, this actually behaves as if it was a tree, where each one of the nodes is annotated with a name, in this case category or a name, and a value, an arbitrary value. And for this one example, for projects, the value is actually a budget. But instead of a budget, you could have a list of people that are working on it. Instead of that, you could have a summary of all the information that you're doing. You can have many other things, because this is basically the same as a tree-like structure. You just didn't realize it. So if you ever have a data structure in your code that looks like this, it may be worth looking into the arrow recursion. Arrow recursion is a really advanced module that is used mostly for you if you want to take a look at something that looks like recursive data structure, trees, and everything else. So if these concepts are alien to you, do not worry. Again, you don't have to take the whole arrow into your program. This is just one of the parts of it that works for a really specific kind of use cases of people. So we're trying to include not only the people that work on Android, not only the people that work on backend, maybe people that work on tooling, that work on ASTs, syntax trees and everything else. So everybody should be able to get some value out of this. And I want to thank Ethan Smith, by the way, because he used to have this as a separate library, even though if he was using Arrow, and he decided to join and merge with us, and we are going to be shipping the module real soon. So another big problem that we're trying to tackle is going to be constructing and deconstructing data, or serializing and deserializing data. So this is a hard problem. We are seeing that even JetBrains has their own serialization library, that we have Moshi, we have many of them, and most of them rely on like annotation processing or like runtime evaluation, all that stuff. So we're trying to come out with our own solution where maybe we could get a generalization for this concept. So what we're going to do is to take the data, your data classes, and destructure them into something that is called structural types, something that is not like your regular data with the same name, but it has exactly the same structure. So let's see an example. We have something that is an account. The account has an ID, it has a balance, and it has like a name associated to it. And this account could actually be exactly the same as a triple of an integer, of a string of an integer. Or it could be the same as a heterogeneous list, a list of multiple different types, where the first type is an integer, the second type is a string, and the third node is actually an integer. So all the three of these are isomorphic. They are not the same because account has a name and has a name for the fields, but they could be transformed between each other without any information loss. So we can give you an annotation processor based on Eugenio's work that allows you to do this deconstruction. So you can just say, my actual account class is a product. It's a product of the fields, like in math. And you can just say, I want this account actually to be tupled, because I know how to serialize and deserialize tuples. Or I want it as an heterogeneous list, so I can traverse every one of the fields, do something with it, and then go back into the original transformation. Or maybe I can just add two accounts together. Because I understand the structure of the account and I know how to sum numbers or strings, I can just give you a way of summing two accounts together. And it's the same if you have multiple accounts and you can add of them together, because it's just basically like aggregation of every one of the elements. So this is a really early days module. This is something that shipped not that long ago, and we're trying to expand to also support CO classes. But for the moment, it's only for data classes, and it's only for this kind of deconstruction. This is another big selling point, and this is something that we have put a lot of interest in, which is trying to help people make their abstractions, their things that are already in the code base, have extra behavior. So sometimes maybe you're not able to use RxJava, but you wish that your Guava future would have some of the operators. Or maybe you have some of those operators and you don't want to implement map for every single, index list, index map, and everything else that actually doesn't have the map operator because it's from an old library, or maybe something that you wrote inside your company, or everything else. Or maybe you have something like, okay, the shapes of the generics don't quite fit, so I have something that is actually a tuple of a list of an option of a pair, and I want to make it into an option of a list of a tuple. So those kind of transformations, they are limited. There is a very small set of them, and they can be abstracted over. And the last one is the lack of familiarity with some of the syntax. So you have something that is get user by ID, flat map, or observable.merge, another map, and everything gets a little bit like triangular and everything else, and we can provide abstractions to work over that. So let's dig a little bit deeper. Extension interfaces. So the same way that you have extension functions that exist at a global scope, you can have a single interface that actually gives you extension functions as long as you're within that scope. So you can just say, hey, here's my extension function called hasNetwork.run, and actually within that run block, you should be able to call network functions. So you have extension functions that are actually scoped, which means the interface that you're creating to access those extension functions can be parameterized to something. It can be a generic, it can be having a value, it can be some more advanced stuff that we're going to discuss in a second. So some of the ones that we are already providing of these extension interfaces on the Arrow library, one of them, if you implement map, we're going to give you 6 more extension functions. We give you a way of adding 2 elements together as if they were a tuple, for example. If you implement fold, or in this case fold left, you get 17 new methods where you're able to transform your data. And you only have to implement one, fold left. 17 new methods, where you can do, and each one of them gives you something different value, a way of moving like all the structures that are within your list or your maps or your optionals and everything else. Flat map, you know this one, is the one where you say, hey, I'm going to continue my execution into a different place. We can give you another 8. And also, we give you access to comprehensions. We give you access to coroutines or coroutine syntax for your current abstractions. So let's see some examples. New functionality everywhere. I'm going to be using examples from within the library, but you can imagine you can apply this to something else. So each one of them. Top, we have an option of an element, and I want just the option of an element. For that, I will need to flatten it. And flatten is a function that you can already do if you have implemented flatmap. So as long as option implements flatmap and you're inside one of those extension interfaces, you can just do option.flatten, and you're going to get the smaller version. Let's say you have a try of ID, a try of name, and a try of count, and you're going to put the 3 of them together. But if one of them fails, you want the whole thing to fail. So basically, you're aggregating 3 different values, executing them, or unwrapping them, and then aggregating the results as a tuple. That's called an applicative, is the name of the extension interface, and the function that you want to call is called tupled. Let's say you have a set, and the set actually has a search function. So it goes from user to Boolean, and then you get an option of a user. We can give you that function, as long as your set is implementing foldable. And the last one, and this is probably a fan favorite. This is something that we've talked to many people, and they come to our chat and everything. It's like, hey, how do I do this? And it's actually a single function. I have a list of deferred. I have a list of coroutines. And I actually want a coroutine of the list of the elements inside. I have an observable, a list of observable operations. And I actually want a single observable that aggregates all the results as a list. I have a map, and the map goes from ID to an either of an error or a user. And what I actually want is an either where if any one of the elements inside the map is an error, it's going to error. Else, it's going to aggregate all the elements inside map. And that's a single function. It's called sequence. You go to listk.sequence, you pass the name of the abstraction that is inside, basically, and you get the other one. You don't have to write the code. I don't have to care about like traversing through the list and waiting for each one of the elements, getting the result, putting it in a tuple, which one is going to return first. I don't have to write any of that code. It's a one-liner. And we have many of these one-liners, and the only thing that you have to do is read the type signature. You say, I have something that looks like this. I want something that looks like that. Let me scroll through the library. Let me scroll through the documentation until I find something that does that. And this is tested. Like whenever you implement one of these extension interfaces, we give you a test suite with hundreds of tests for each one of them. Well, few tests that run 1,000 times. So, okay, let's say tens of tests, and each one of them is going to give you the assurance that this is fulfilling your expectations, basically, that it has a stable interface and it has a stable value. We also give you access to comprehensions. So if you implement flatmap, if you're a monad, we can give you access to coroutines and async await syntax. So for us, instead of coding async await to avoid like name collisions and all those things, we're calling binding and bind. So you're going to say, hey, we're going to have a block that is called a binding catch, just like async, and we're going to capture all the exceptions inside, and then I'm going to get the users by ID, and I'm going to bind it, which means I'm going to flat map it. I'm going to get the result, which is a user. And then with that user, for each one of the friends of that user, I'm actually going to get, their profile information. And I'm going to put it together, and that's the information that I'm going to return. So this is the same snippet as the beginning, the one that is flat mapping information, but this syntax actually looks like imperative code. It looks like coroutines because it's coroutines behind the scenes. But we can give you coroutines for every single one of your abstractions as long as they implement the function flatmap. Simple as that. It works for everybody. It's ridiculous. I don't know. The first time that I saw this was like, mind blown. The other thing, and this is a little bit more of an advanced concept, is that you can still do coding to the interface, the same way that you normally do with Java. So if you have a function that actually requires something to be foldable, to be a monad, and also to have like access to the network. I think I put network in there. Yeah, provides the network. And I actually need equality, which is a simple extension interface that has a single function that allows you to compare two things. So instead of using object equals, you can compare to things by ID, by one of the fields, the sum of their elements. It doesn't matter. It's the same as a comparable. And you can say, OK, I have a single function that actually depends on all these elements, and each one of them can be fulfilled for different values. So they can be fulfilled by try. So you can just call request teams with the try dependencies, and you're going to get a try back. Or you can call the same function with an either dependencies, and you're going to get an either. You can call it with an option, you're going to get an option. So basically, you're abstracting over the containers rather than on the context. And you're also abstracting over the functionality that these containers have to have for you in order to use it. So I won't be able to use it to use try if it doesn't implement my extension interface, which is the same like coding to the interface that we do in Java. So this package is actually called Arrow type classes. Type classes is the technical name for the language feature that is the extension interfaces, and basically each one of them has between 1 and 3 methods that you have to implement to get the rest of them. You get all the scope information, you get all the scope extension functions, and you can do the replacement for these generic elements. And each one of them gives you a test suite because it's based on math. The ones that we are providing in the library, which is not all of them that exist, but the ones that we provide, each one of them has a really tried and tested test suite that is based on math. So if you have something like flat map, you know that A flat map, B flat map, C has to happen in that order of events. It cannot happen in any other order. Why? Because that's the laws, that's the test, that's the thing, the information that we're going to give to you. And that happens for everything that we have implemented. Problem is, OK, so we have all of this is actually a graph representation. Each one of the blue nodes, like the small ones, is a type class. It's like an interface that we are providing in the library. And the lists below them are all the data types, or the try, option, map, I don't know, set, and everything else that implement that specific type class. These are the ones that we're providing by the library. There's a lot of them. OK, I want to use it in my program, but I want to have to remember, I want to like deal with them manually, and that's completely OK, because there's a lot. So we provide a way for you to do dependency management. We have something that is called the Arrow instances, which basically means we're going to give you all of these, but it's optional. This is not part of the core. This is not part of the data. This is a lot of methods. This is weight on your application that maybe you don't want to put in. We give it to you as an option. And we allow you to do dependency management on it, so you can add this dependency, and also you can give the Arrow Dagger modules. So you can use Dagger to inject each one of those that I showed you before. And you can just say, my whole class actually depends on this interface. That's the scope of my extension. And I can inject it using Dagger in the constructor. Simple as that. The other modules, I'm going to skim through them because my time is not that really great. One of them is called Arrow Effects. Arrow Effects tries to abstract over RxJava, coroutines, all these stream libraries, all those things that do like I/O operation, tasks, everything that has a thread on it basically probably is part of this module. And we're trying to find an abstraction that describes all of them so you can use them interchangeably. You can go to the interface, and then you can do the application. So you can have get user friends for observable, get user friends for I/O, get user friends for deferred. And each one of them is actually the same implementation behind the scenes. The other module, and this is very advanced, is called Arrow Free, which is a way of doing an interpreter for operational DSLs. So the DSLs that Kotlin has are constructional DSLs. You have something like HTML, right? You define your DSL, it executes, it returns you a value. In this case, the DSLs that we are doing here, they return you a description of a program that you have to run, that you have to interpret afterwards, as if it was like a meta language embedded within your program with a set of operation. This is really advanced concept. Like, this is enough for like 10 talks, so I'm just going to go through the next one. But so you know, for the people that like these advanced constructs, so they understand it, or they come from like other backgrounds, they're available in the library. So with all of this, these are the basics. This is the core. This is the stuff that we expect other people to use to build in. Most of these are complete, mostly stable, and available right now. So you can use this in your libraries, you can use this in your applications if you want to replace these small use cases or those large ideas. So I'm going to go through several examples of how we're dogfooding our own library and how other people are using them. So the first one is called Ank. Ank is a library that is used for verifying snippets of code. So let's say you have the documentation has snippets, and you want to run them, and you want to see the results, and you want to actually embed the results on the docs themselves. This way, you make sure that the documentation is always up to date, that the code is correct, and actually the users can see the results of your evaluation without you faking them. So we use this within Arrow. If you go to the website, to the documentation, you're going to see that many of the snippets actually have the results below them. So if you say, hey, list.map 1+1, this function composition and everything else, we're actually running them while we're building the artifact, and we're outputting that information to our website, and that's the real stuff. So we know that our documentation is mostly not up to date, except for a couple of problems with the executor, but that's fine. And basically, this library, even though it's in organization, is mostly managed by Pablo Guardiola from Mapbox, and he's doing a really great job with it. And this uses actually Arrow free. So this is a really good example of like those interpreters. And it allows you to do compilation of Kotlin and also Java. So you can use that today. This is available. We have Helios. Helios is a screaming fast JSON library that 47 Degrees is working on at the moment, and it attempts to have a DSL that is similar to what Optics do. Optics were the one where we were trying to access all these immutable fields. So we want to do that for JSON in a type-safe way. Not like JS Dynamic, which can throw exception, it works like JavaScript, but in a way that is as type-safe as possible. It is fast because we have Forta parser that comes from Scala and it's like supposed to be really great, but it's still pre-production. It's alpha. We have Collect, which is a library that is going to be used on top of your network stack to do batching of requests, to do any kind of parallelization, any kind of caching, all these kind of great ideas about threads and everything else that most of the time you don't want to worry about within your library or your application. Another one is Core. Core actually uses core and data to do use cases for like a clean architecture. So it's an example of a clean architecture library that is using parts of it, parts of Kotlin, parts of Arrow to define some of the APIs. We have Kessel. Kessel is a library that tries to do parser combinators. So if you're trying to write tooling that analyzes code, that takes a look at like ASTs, that is trying to do a compiler or something like that, we have something that is a parser, a parser combinator. It has really advanced concepts. It actually tries to do stuff from like new papers and everything else, and it's really cool. The maintainer has been really nice, and he let me put this on the slides, basically. And it uses, again, information about core and data. We have something that we would like to do in the future that is called the Arrow streams. So if Arrow Effects cares about things that return one value or that do tasks, Arrow streams cares about reactive streams, information that comes over time in a way that we can abstract over the operators. So maybe flat maps works for one element, but things like merge or sep have to work for multiple elements that come into a stream. So we want to have an abstraction that actually covers all of them and allows you to run them using any of your effects. So even if you have something that doesn't allow streaming, but still allows you to do tasks and like multi-threading and everything else, you could use that to create your own streaming library. And we will also like to have something for Android. This is a little bit ambitious. This is really early stages. This is something that is in our mind, but has not crystallized yet into something. So if people have ideas of how they would like their applications to work with a fully functional API, with everything from top to down, including launching activities, including managing context and everything else, we're happy to hear. We have our own ideas, but this is a pointless exercise if we do it in isolation. So the last part of the talk, and I have 55 seconds left, maybe one more minute, can I? Yes, awesome. How we share this understanding. So I don't know about some of this. I'm not going to say most of this because that will be, but I don't know about some of this. I'm learning. As I'm implementing them, as I'm going through the documentation, as I'm going through all the libraries and the examples, when I'm trying to implement them, I'm learning how to write functional code. This is not me being like a super genius or anything. I started the project like a year and something ago, and I didn't know about many of these things. And as I was implementing them, as I was learning, I started, trying to get an understanding, trying to build that functional, ideas in my head, and actually implementing them helped me a lot. So we want to share that understanding that is fraction between different people and different communities and different modules back to you. So we have the Arrow docs. As I've said before, they are type-checked. It's a large community effort. There's like hundreds of documents that have to be written. Each one has to have good examples because we are actually trying to teach you how to do functional programming, like even from the starting level all the way to really advanced concepts. And sometimes they get a little bit mixed, but we're trying to get it better a little bit over time. So we have tens of contributors, people that are adding their own ideas or their own understanding, and they are maybe learning just so they can write the document. We have a video series. So on top of some of the actual documents, 47 Degrees is creating every week a new video that explains the same information that is on the doc. So they just go through a couple of examples, they go through some of the important parts of it, and basically give you a greater idea of where you can use it. We also have a bunch of talks and books and even courses right now that are trying to cover these all functional concepts and how we can use these ideas. So we have the functional, Kotlin Unpacked, which is a book that was released at the beginning of the year, but we also have three courses actually in Caster.io, Functional Hub and Udemy. The Udemy one we didn't even know about. We show up one morning, it's like, shit, there's a new course about Arrow. Nice, people are liking it, people are using it. And finally, I want to give a big, huge thanks to the community. Because again, this is not an exercise in isolation. These people work for all the companies. Each one of them does different things. We come from like Scala, Android, Java, backend, frontend, everywhere else. And everybody's adding a little bit of themselves, all the stuff that they know, to the common pool of understanding. We are very active in a Gitter chat. So I'm going to say like, several hours most of the time, maybe half a day, depending on how our timing is, because everybody's pretty much based in Europe, except for a couple of guys. But people go there, ask questions, they thank us, they go giving talks with all the stuff that I help them with. And it's the same case if you're in the Kotlin lang Slack. We have a channel called Arrow, and we're really responsive in there. So you can just go there, ask your questions, and we're happy to help. Beginner, intermediate, advanced, shit on the library, we don't care, like, it's fine. Just come talk to us because we want to help you, and we want to have like all of this together. So that was my 2 minutes extra pitch. This is the library, it's called ArrowKT, or Arrow. Thanks to the contributors, and thanks to the conference for inviting me. So thank you much. Cool. I'm going to get some water, ask the questions meanwhile. If there's time. Is there time? Okay.
Do you plan to have persistent data structures?
Yes.
Like in Clojure?
Yes. We had somebody working on those. We had some family issues, and basically the project kind of fizzled out a little bit. We are super happy to retake it. And we're actually looking for somebody that is willing to drive it. If not, maybe at some point we'll just take out the Clojure Java library and try to port it, because I've tried to do that in the past and it wasn't like a lot of work. So yes, this is something that we definitely would like to have as soon as we have like the bandwidth to do it.
That's amazing, thanks.
Thank you. But comments are also good. Like, it's fine, it's feedback. It's helpful. No? Cool. Well, thank you much. Thank you again.